Good morning, professors from the scientific committee. I am Edison from Queen's College, and we are very honored to be able to present our research projects on the generalizations of the no-free inline problem. So we'll first discuss what the no-free inline problem is, briefly. The original no-free inline problem discusses the issue of how many points can be placed on an evenly spaced n by n square grid, such that no free points are collinear. The most trivial result in the research of this problem is that at most 2 endpoints can be placed, with non-collinear, as if more are placed, then by the pigeonhole principle there would be more than 2 points in some row or column. And so far, for solutions of 2n have been found for all n tested. Just a few weeks ago, they were tested up to n equals 58, and here's an example of a solution for n equals 10. It is, however, ever unclear if solutions for 2n will continue to exist for larger and larger n. Here are some key papers we'll be referring to throughout our research. The most important one is the one in 1968 by Guy and Kelly, who used the heuristic to conjecture that solutions with 2 endpoints are quite limited. And as n becomes very, very large, then it's expected that solutions will only exist up to about 1.8 endpoints. The second result was from 1975 by Hall and others, who used a constructive proof to show that solutions with a little fewer than 1.5 endpoints have to exist for all n, which provide both the upper bound and the lower bound for the problem. In our research, we investigate 2 generalizations of the problem. First, a rectangular n by n grid, and we've generalized the results from Guy and Kelly to the grid. We first conjecture that placing the maximum of 2 endpoints, which we'll prove later to be 2m, is only feasible when n is larger than about 1.2 m. And we also extend their conjecture on the maximum number of placeable points, which we'll prove to be about 1.8 square root mn, given the heuristic. And we also investigate the key problem on the 3D grid. And we first arrive at an asymptotic number for the number of 3D collinear triples, which is an important step in the heuristic solution. We also conjecture that a weak version of Guy and Kelly's conjecture holds in 3D. However, we show that stronger forms will fail. We will first cover the results for the rectangular lattice. We first provide an explicit construction for solutions on the grid, and then provide a heuristic estimate for the number of points that can be placed on the grid later. And so the most basic result is that at most 2 endpoints can be placed on the n by n grid, with there being no collinear triples. The reasoning is the same. It's based on the pigeonhole principle. And a lower bound for the number of points that can be placed is harder to arrive at. However, we can extend the methods developed by Hall in 1975. And we can show that for n a little larger than 2m, we can always place 2 endpoints on the grid. Here's an example of our construction for m equals 8 and n equals 21. And as you can see, a key feature of this construction is that at most 1 point is placed on each column. And so a simple corollary of our construction is that if we have an m by n grid, where n is larger than m, then a little fewer than n points can always be placed on the grid with no free collinear. And now we'll look at the heuristic solution. Our method is based on, again, Guy and Kelly's approach, which estimates the probability that p randomly placed points on the lattice are all non-collinear. This method is based on counting the number of collinear triples, which is the number of all sets of 3 points in the lattice which are collinear. And so, therefore, the probability that any 3 randomly chosen points are non-collinear is equal to this expression here. Now, suppose that p points are randomly chosen from the grid, and we want to find the probability that every single choice of the 3 points among the p points is non-collinear. And Guy and Kelly's heuristic was that, in particular, was that any 3 randomly chosen points from those 3 points being collinear, those events are not correlated. And so the total probability would be equal to this whole expression here. And from which the expression for the expected number of solutions follows quite easily. And the heuristic was that solutions should exist only if this quantity here is greater than 1. And we found, during our research, we found that there was no data supporting the heuristic, and so we ran empirical tests. And we found that as n increases, the relative error between their approximation and the experimental probability that points are non-collinear tends to decrease as n increases. And moreover, their heuristic is always an overestimate of the number of solutions in our tested regime. And so we can be quite confident that their heuristic provides a good upper bound. And now we'll move on to the strategy for counting collinear triples. We first consider lines of slope q over p only, and we categorize all unique lines by how many lattice points they pass through. And we use this information to count the collinear triples with slope q over p. And finally, we sum over all slopes to obtain the total number of collinear triples in the grid. And here we take a look at the categorization step. You see here, this is an example of the categorization for lines of slope 3 over 4. And you see each point is labeled with a number. So if I draw a line through this point, you'll see that it passes through 5 other lattice points, which is what this number means. And there are 3 obvious structures to the categorization. You see these blocks on the corners, these blocks on the diagonal, and everything else left over. And you can prove that each of these structures corresponds to one class of lines. And so when we start the counting step for the number of lines, you see that we first define R to be this number, and we find that lines passing through less than R lattice points are equal to this number, which corresponds to the blocks around the corners. And lines passing through R plus 1 lattice points correspond to the blocks on the main diagonal, and everything else left over corresponds to lines passing through R points. Now, for each unique line passing through I lattice points, there are I choose 3 ways to form collinear triples from them. And so the expression for the number of collinear triples of slope q over p is as follows. And finally, we use sum over lines of all slopes to obtain the total number of collinear triples in general. The complete analysis of the summation involves quite a bit of number theory, and a fully rigorous analysis of this is given in Appendix A. And following Guy and Kelly's heuristic, we take the number of solutions to the rectangular no-free line problem to be equal to this. And the cutoff points for whether solutions exist or not is, again, omega equals 1, or ln omega equals 0. And so if we want to find the conditions for the maximum number of points to exist, we set p equals to m and solve for n, and we obtain conjecture 1. And similarly, if we want the expression for the expected number of points that can be placed, we fix m and n and solve for p, which gives us conjecture 2. And we repeat the same thing in 3D. Only now, instead of considering slopes, we're considering vectors in general. And again, this condition ensures that we don't double count lines. And similarly to the 2D case, we try to categorize lines, and we again find 3 classes of structures, which we will not detail here, as the structures are quite a bit more complicated. And when we finish the summation, we find that this is the number of collinear triples in 3D. And we look again at Guy and Kelly's heuristic. Empirical testing shows that Guy and Kelly's approximation holds if we place an order of n points on the grid. However, for points placed of larger order, we show that the approximation has to fail. Notably, in 2004, it was proved that an order of n squared points can always be placed on the 3D grid. However, if we apply Guy and Kelly's heuristic, we find that they predict an order of only about this. They predict that only this many points can be placed on the grid. And so the heuristic has to be incorrect as more and more points are placed. And as a matter of future research, it is possible to find perhaps better heuristics to provide a better estimate of the number of points that can be placed on the grid. Thank you.